Today's lecture is because I can't be in class this morning, but I wanted to give you something that will help you bring your C programming skills back into the front and also give you a very specific opportunity to interact with MPLAB and start getting comfortable with it. So first I'm going to go over some logical and bitwise operations related to C programming, then look a little bit at loops. Finally, we'll go over to MPLAB, and I'm going to give you a template to a program to copy into a program on your computer, and then you'll have some exercises to go with it that you'll have to solve. But I'm going to walk you through it and show you what's going to be involved. So let's start by looking at some C programming. Down and dirty, what's the very beginning? C arithmetic operators. So which operators are we looking at? Plus and minus, you've been doing that since first grade, probably earlier than that. Double plus and double minus signs, this is the increment and decrement. So I plus plus says whatever I is, if it was 4, now it's 5. Or if it's decrement, if it was 4, now it's 3. Multiplication and division, we use the standard symbols. MPLAB knows how to use them. Shift left is shift right. We will take a look at very helpful functions, and this makes math a whole lot faster in a microcontroller. Bitwise and or and exclusive or. Bitwise complement. And that'll be the first set. We'll come back and look at some others in a few minutes, or some additional information in a few minutes. But let's look at shift left and shift right. Basically, it's a binary operation, not hex, and it moves by one moves by one bit position. So that if this is our original value, going from B0 on the right to B7 on the left, when we do the shift right by 1, then we're going to bring in a 0. We'll bring in a 0 from the left into the most significant bit position. We'll shift bit 0 off the right end, it's gone, and shift everything else down by 1. Shift left is a similar operation, except going in the opposite direction. Everything goes to the left by 1, but the piece that's in the bit 7 position gets shifted off, and a 0 gets shifted in as B0. So let's look at the conditional tests that we're going to be using with our operations. Double equal sign means equal. Exclamation point and equal means not equal. Greater than or greater than and equal, symbols you're very familiar with. Same for less than or equal. The double and for logical and. Double pipe, the logical or. Exclamation point is the logical negation. Now catch that this is logical negation, not bitwise. So if I say that I is equal to hex A0, notice that 0x, that's a symbol we'll use to designate hexadecimal. We use a 0b as a preference, or as a prefix when we're doing binary. And if we're doing decimal, there'll be no prefix. So if we set it as a hex A0, if it's a logical operation, it's either 0 or it's not 0. So if it's not 0, it doesn't matter if it's 1 or 2 to the 23rd. It's still true. And that's the meaning of a positive value, or a non-zero value. So in this case, if we expand it, that's hex. Binary, it's 1010 for A, and 0000 for the 0. Notice that we can group groups of 4 as we're transferring between binary, between binary and and hex. But notice also that exclamation point I isn't the same as complement I. Exclamation I, that's logical, that goes to 0. But complement I 0 goes to F, and an A goes to a 5. So that 0 becomes 0, 0, 0, 0, complemented as 1, 1, 1, 1. 1, 0, 1, 0 becomes 0, 1, 0, 1, which just happens to be a 5. Well, let's start by defining some 8-bit values. A, comma, B, A, LTB, that's going to be A less than B. Then the next one you can probably interpret A equals B, A greater than B, or A not equal to B. So from here, we'll set A equal to 5 and B equal to 10. So the first thing we'll look at, A less than B equals, in parentheses, A less than B. Now notice that A less than B is not a numerical calculation, it's simply a logical structure saying A is less than B, and that's either a true statement or it's a false statement. In this case, a 5 is less than a 10, so A less than B means that the value now of A less than B is a 1, because that's a variable. Similarly, to say that A equals B is equal to the test is A equal to B, notice the double equal signs, and the answer is 0 because A does not equal B. So this is a logical test. A greater than B is equal to the logical test is A greater than B, and the answer is no, or a 0, so A greater than B gives us a 0. A not equal to B is equal to the logical test A not equal to B, and the result is a 1 because that is a true statement. Now let's look at some other options. A logical OR with B versus a bitwise OR with B. One negating B, or B complement B. So let's do something with them. We're going to set A equal to a hex F0 and a B equal to a hex 0F. You can see we're up to something already. So a logical A and B is equal to A and B. Logically, they're both true statements. It's not that they're equal, it's that they're both true. They're both non-zero. A bitwise with B is a single AND sound, and the answer is 0 because it's not. They are not the same bitwise. F0 is not bitwise the same as 0F. If we logically OR A and B, now this is logical, the answer is going to be a 1 because this is non-zero and this is non-zero, so this is true or this is true, therefore it's true. Bitwise OR A and B, we're going to OR A, which is an F0, with 0F. F and 0 gives us an F, 0 and F gets us an F, so the answer is FF. But this is bitwise in contrast to logical. So catch the difference between these two ORs. That's subtle. The same with a logical AND and a bitwise AND. Logical, double ampersand, bitwise, single ampersand. Logical, double pipe, bitwise, single pipe. Now let's do the next pair, which is going to be logical negate. Well, logical negate says not B. If B happens to be true, then its negation is false, or 0. But complement of B, if we start with a 0F, everything that's a 0 here, 4 zeros becomes FFFF, and 4 F's becomes 0, 0, 0, 0, so our result is an F0. So those are some bitwise versus logical operations. Now let's look at some conditional statements and see what we can do with them. The if statement, you're going to find a great deal in our semester. We've got an if, then a test, then open the parentheses and say what we're going to do if we pass the test. If we don't pass the test, then we go to an else. And again, open the brackets, close the brackets, else, open the bracket, close the bracket. And again, if this is true, we'll do this. If this is false, we'll do this. And we don't have to limit ourselves to a single statement. We can use those logical expressions that we just looked at to make compound if statements or compound else statements. So let's take a look at some options. If I is false or I is 0, then we're going to do this, j equals I plus j. Just very simple code, but you can see if I is false, then we're going to do this. Here's another way to write the same thing. One of the interesting things about C and other languages is there are many ways to express a feature. So if I is equal to 0, then we're going to do this, j equals I plus j. Now we can turn it around and look at the other side. We looked at the if I is false, now we'll look at if I is true. If I is not equal to 0, then do this, j equals I plus j. Again, the alternative way to write it, if I is not equal to 0, meaning if it's true, then j equals I plus j. Same thing, straightforward. This one will catch you sometime during the semester. I can almost guarantee it. 2 equal signs is an equality test. Does A equal B? But a single equal sign assigns. So if I say A equal B, I'm saying B's value is now taken on by A. Now watch this closely. I say if I equals 5, j equals I plus j. Bingo! We just hit the same problem. We used a single equal sign instead of the test operator. So we've said I equals 5 here. That makes a true statement, but it's not correct statement. So it's always going to execute. Here, if I is equal to 5, this is the test, then we'll do j equals I plus j. This one always works, always runs, because that's never false. That's an assignment that I equals 5. This one tests to see whether I is equal to 5. Now let's use the ampersand, the AND function. Bitwise, single ampersand, logical, double ampersand. The double ampersand says it's either 0 or it's not 0. So what's that lead to? If I is not 0 and j is not 0, then do something. Here, if every bit of I matches every bit of j, then do something. Notice the difference between the two. Now if we know that I is 5 and j is 5, then bitwise they're going to be identical. But if I is 5 and j is 6, bitwise they are not identical. So here's an example to test that with. I'm going to set I equal to hex A0 and j is equal to hex 0b. I and j using the logical operator. I is not 0, j is not 0, therefore we get a 1. But the other piece, if we bitwise compare I and j, it's different. They're not bitwise identical. C, a bitwise logical versus an OR logical, or logical OR. Single pipe, it's a bitwise OR. Double pipe is a logical OR. Again, logical, it's either 0 or not 0. Bitwise, it's going to be bit by bit. So I say if I is not 0 or j is not 0, then do something. Either one, not 0, and it works. But if I go with a single pipe, if I, bitwise, or j are, if either of them is non-zero, then we'll do something. So here we've got A, 0 is I, 0B is J, so I or J is going to give us a 1. Because logically, either one of them true, they're both true, so it's true. I or J, bitwise, A versus zeros gives us an A, B versus zeros gives us a B. So a hex AB is the bitwise function. Now let's take an if and let's put it into several different constructs just so you can see some examples of putting it to work. If, and then I give it a test. Then I give it the instructions if it passes the test at the if body. Otherwise I'll do the else, and I'll do the else body. Now the else section is not mandatory, it's optional. I can stop if I say if, here's a test, then do something. I don't have to say else, but if I do, here's the structure. So I can say, define k as an integer. If k is true, then do this. If k is not true, then don't do it. Catch, we're not doing the else piece. But if k is true, we'll do something. Now here's the test. I've got two integers, k and j. If k is equal to j, here we're doing a test. If it passes, we'll do the if body and go on from there. Here's an equivalent. K equals, if k is greater than j, do the if body. Otherwise, don't. Just keep on going to the rest of the code. And we'll put two together. J and k. If k is less than or equal to j, then we'll do that if it passes the test. Otherwise, meaning k is greater than j, we'll do something else. So here we have two choices. If it's less than or equal, if it's greater than. All defined by the if and else. So that's the if structure. Now let's go on and look at the switch statement. And we can put a series of if statements together. If, we get a test. Else if, a different test. Else if, a third test. Else, and this is the default, do this. We can turn this into a switch statement. We're going to switch. We've defined U8I as our variable to switch on. If U8I is equal to 1, then we'll do the first one. If U8I is equal to 2, then we'll do the second one. And notice the break gets us out of case 1 and out of the case structure completely. As soon as we hit a break, we're finished this switch case. It's the same as this if. As soon as we execute one of these, we're not going to execute the remaining. So here, if we execute this one, then we won't execute the rest. The break takes us out. Case 2, if 8i is equal to 2, or if 8i is equal to 3, or if it's not equal to 1, 2, or 3, then we'll do this one. And the switch statement and the else if are exactly the same. Now let's look at the while statement and the do while statement. In the while statement, as long as this is true, we'll continue to do this. Putting it into practice, while, as long as k is greater than j, continue to do the instructions in the while body. But as soon as k is not greater than j, we move on to the rest of the code. Similarly, there is a do while, and it's structured with a do, open the brackets, instructions, while, and then we give the condition. So in this case, as we're going to do whatever's here, and then test is k greater than j, go on to the rest of our code. This is intriguing because the while body is only executed if this is true. It's not executed if it's false. In contrast, do and do this before we do the test, we're always going to run it once. We'll always execute it at least one time. So that's while and do while. Again, two very useful functions. For loops are another structure that you've been taught, and they are just another way to do a while loop. If I say while I is less than or equal to 10, k is equal to k plus j, and then I'm going to increment I and go back through the loop again and see is I not equal to 10. And we'll keep doing this, and if I start at 0, and it's going to go until it sees a 10 and it won't execute the 10, it'll break out at that point. It's going to run 10 times because at the end of this, I equal to 0, increment I, now I is equal to 1, run this, increment I equal to 2, and so on until it equals 10. This is exactly the same operation as using a for loop. I can use a while loop, I can use a for loop. For, start with I equal to 0, I not equal to 10, I plus plus. This is our start, this is our destination, this is the increment at the end of it. K equal k plus j, same function, and then automatically in the for loop, the I plus plus is here, so here's where our increment goes. We're still going to do the test, and they both break out after 10 runs. Quick review of C programming. Now we're going to stop here for a bit, and we're going to go on to an MP Lab exercise.